before. Hey, Saga, I've not noticed. Wow.
Hello, this is a test. Testing the sound. Please check the sound. Testing the sound. It is very, very clear. Testing the sound. Testing the sound. It is very, very clear. It is very, very clear. Testing the sound. Is it working? Testing the sound. Because YouTube lagged a bit. Testing the sound. Testing the sound. Testing the sound. Testing the sound. Tonight I'll come to you. Hurry. Hi everyone, welcome to today's YouTube tutorial session. Good evening, and hopefully we make the best out of the evening. So our next paper. Our next paper is our power system analysis. So we're doing power system analysis. Taught by Professor Oche. Yes. So this is what we're writing tomorrow. Now, okay. Sure. Now, what are we expecting in the exams? We are expecting all content from Unit 1. All contents in Unit 1. Which means we are talking about stuff like the importance of load flow study, specifications of the load flow problem, then how to compute the power inputs and all those things. And then we also saw the Gauss-Seidel method, the Newton-Raphson method. Then we'll look at Unit 2 up to symmetrical fault. Unit 2 up to symmetrical faults. So here we're talking about stuff like causes of faults. Then we'll see why we're doing fault analysis, why fault analysis. Then we'll see some types of faults. Talk about, so please, all these things are things that you are supposed to read, because it's MCQs, meaning you have these reading questions in it. Then we'll come to the symmetrical fault, how to deal with symmetrical fault. And we say we have two ways. We have the direct method and the Thevenin method. So direct method is for solving unloaded, and then these two are for solving loaded. So for loaded, you can use either direct or Thevenin's method. Okay. So yes, so basically here is what the Lord wants us to look at. All right. So we've already done a first stream talking about the principles. We've spoken about Newton-Raphson, Gauss-Seidel. We saw how to draw the fault, how to draw the diagrams, right? We worked on that in the previous video. So if you've not watched that, kindly do so, and then come and continue watching this one. So today's session we'll be using questions. We'll be using questions. So we're using some questions to do what we are supposed to do. So the first questions we'll use are these questions, the online quiz we did. So we'll start from here. So look at these online quiz questions, then we'll proceed from there. So let's start. So these are questions on Unit 1. Okay, these are Unit 1 questions that we'll be looking at today. So this is a first question on the admittance matrix. So this is a 3-bar system, right? We know that in the admittance matrix, what goes here is admittance attached to bus bar 1. What goes here is admittance attached to bus bar 2. And what goes here are admittance attached to bus bar 3. So now we want Y2, meaning that all admittance is connected to 2. So you come here, anywhere you see a 2, you consider. So you are considering this row and that row. So you're looking at how to find Y22, right? I'm saying Y22 is equal to all admittances connected to sure. So we are seeing Y22, right? Which is impedances connected to bus 2. Let me cover this thing. Fantastic. So we said impedance is connected to bus 2. So anywhere we see a 2, consider it now. Lines, transmission lines are modeled in 2 ways, okay? They can be modeled as short lines. So as a short line, a transmission line is made up of a resistor in series with an inductor. So for many of the calculations to do where we see Z is equal to R plus JX, we are considering the short line model. We just need the R and the J as our impedance, and then our Y will be 1 over impedance. Now here we have to model it. Anytime you see the YC over 2, it means that it's no more a short line, but it is a medium line. A medium line is modeled as this R and X, but then it has capacitors connected, 2 capacitors connected like this. It has 2 capacitors connected like this. So this capacitor has capacitance YC over 2. That's capacitive admittance YC over 2. And here too also has capacitive admittance YC over 2. So this is the model we'll be using to do this analysis. So now between bus 1 and 2, so we see that we are looking at all impedances or all admittances connected to bus 2. So let's say I have bus 1, I have bus 2, let's say I have bus 3, right? Sure. So there's also another impedance from 2 to 3, which also goes through another medium line. Are you getting it? So now let's see. So connected to bus 2 here, I'm having this impedance, which is this. Then I'm also having this YC over 2 here, connected to bus 2, which is this. Then the one coming from 3 to 2 also has, so let's say from 3 to 2, I'm having another resistor and this connected to bus 2. That is this. And then it also has its own short line. It also has its own short line connected. So that also give us, it also has its own medium line equivalence. That also give us plus this. So if you're adding, we'll sum this, and this all together. So please kindly sum them together for me, Papa. What's going to say? So we are getting 4.17 minus J 12.4 minus J 12.4. So that's it. All right. So that's how you go about it. Okay. Sure. Let's move on. The next question. Find Y32. So we say that we are looking at a medium line, right? Medium line model like this. YC over 2, another YC over 2 here. And let's say this is bus bar 2, this is bus bar 3. So what goes into position Y32 of the admittance matrix, this is the position Y32 here, is negative of the impedance between 2 and 3. Negative, don't forget, negative of impedance between 2 and 3. Negative of impedance between 2 and 3. So let's see. Between 2 and 3, I'm having this impedance here. Now take note, if you're looking at between 2 and 3, you don't add these. Why? These shunt capacitors, they are connected directly to, they are not connected between 1 and 3. You see, this one is joined to this node. It's joined to this node directly. It's not joined between 2 and 3. Here it's also joined to this node like this. So between 2 and 3, all I have is just this. So it means just negate this value here. You get it? So it means that it becomes okay. So it becomes negative 2 points. So let me make it bigger. So it becomes negative 2.5. Then here becomes plus 7.5. So that's the answer. So this is the answer. So know that if you are looking at the non-diagonal elements, you don't add the shunt values. You don't add the capacitor values, capacitive admittance values. You just work with the short line parameter like the R and X here. Because this thing is not connected between 2 and this thing is joined to 2. This one is joined to 3. But this is joined between 2 and 3. Alright. Let's move on. So we've seen these two questions here. The next question, you're supposed to find y12. So same. y12. 1, 2 means between 1 and 2. So this. So negative. So negative the admittance between 1 and 2. But without the shunt. Because we said the shunt is not connected between, it's connected to. Half is connected to 2. Half is connected to 2. The other half is connected to 1. So between 1 and 2, I just have this connected between 1 and 2, this value here. So you negate. So you get negative 1.67 plus J 5.0. So this is the answer. Alright. Yeah. Now we have this question here. So these questions are supposed to make us understand Unit 2 very well. Yeah, Jack. I don't have these things. Okay, I don't have this. Use and the rest. Push me. Okay. The next one actually. Right, let's move on, please. So now we've seen. So it means that these three examples have made us to compute. These two examples have made us to compute how to find the admittance matrix, right? How to find that, and even this is even the most extreme case because we're given the medium line model. So the best case is that there will not be any YSP over 2. That one you just consider the R and X values. Sure. Another thing you also look out for, notes, pay attention, is make sure that the values they've given you is admittance values. Make sure it's something you can easily overlook. Like what I mean by that is that make sure that here they've said that the line admittance of a 3x3 is this. If they had given us here to be impedance like this, if here was impedance, that the line impedance of a 3, we will first have to compute the line admittance ourselves. We first have to compute 1 over z to find our y before we come and do our analysis. So that's how confusing you can make it. So yes. So I hope that we can all deal with how to find the admittance matrix. Now let's move on to the next subject. Now we're going to see how to compute the power injected and all those things. Okay, so please, this material I'm using is in the description, so kindly download it from there. The material I'm using is in the description, kindly download it from there, and then you can follow suit. All right, so we've been given that the Y bus of a 3-bus system is a 3-bus system, right? And it has the Y bus of a 3-bus system has the following in per units. So Y11 is given by this. So they've given us Y11. Y11 is 3 minus J9. Y12 is minus 2 plus J6. Y13 is minus 1 plus J3. The voltages at the buses in per unit are, this is V1, this is V2, this is V3, right? Now we are supposed to find the reactive power generated in bus 1. So now we're looking at finding power at buses. Finding power at buses. All right. So now with this one, we are supposed to find what? Find the reactive power. So we're supposed to find KO1. Find the reactive power at bus. We're supposed to find KO1. If you remember correctly, KOG. Yes, you're supposed to find KOG1. KOG1, thank you. So we know that KO1 is equal to KOG1 minus KOD1. So if I find KOG1, I can find KO1 and then add it to KOD1 to give me KOG1. So in the question I was given this SD. This SD in the previous video I said that SD is given by PD plus KOD, JQD. So since you're talking about bus 1, it means this SD1, PD1, QD1. So if you compare this to this, it means that our QD1 is 0.5. This is our QD1. This is our QD1, 0.5. So I have QD1 to be 0.5. I have to find K1 and add it so that I get my KG1. So remember that K1 in this one, use the polar form of the power expression. So K1 is given by negative magnitude of V1 open bracket summation K is equal to 1 to N Y I K V K magnitude cos sine. So sine, so K1 use sine. So sine theta IK plus del K minus del I. So let's expand it. So I get K1 to be equal to minus, so I'm bringing the minus out. So magnitude of V1. Then now I'll come to when K is 1. So when K is 1, I'll get here to be V1. So I showed you how to write it easily from the previous. Sorry, let me mark this thing. Oh, sorry. So Q1 is given by minus. So the last time I showed you how to write it easily, that you are bus 1. So start at 1, V1. Then V1 Y11 sine theta takes this, so theta 11 plus del 1 minus del 1, so that's del 0, but that's 0, so here goes. Then plus you have V1, so you start at V1, then K now goes 2, so V1 V2 Y12, so V1 V2 Y12 sine theta 12, then del, that one becomes 2 minus del 1. It's 3 baskets, so n is going up to 3, so plus V1 V3 Y13 sine theta 13 del 3 minus del 1. Beautiful. So Q1 is given by these. If you check the question, we have all the parameters. We know what V1 is. We're given V1 is this. So as I said, this is used in the polar form. Okay, the expression in this form is in the polar form. So okay. Sure. Hold on. Kindly hold. So you see here, we're given the parameters in rectangular form. So I'm correcting myself. We'll use the rectangular form of the equation. Okay. Please kindly hold. We are coming. Okay. Please kindly hold on, okay? We are trying to check something out. The battery is running low.